In this screencast, we're going to talk about doing Fourier transforms, or really fast Fourier transforms, using the tools that are available to us in Numpy and SciPy. So to begin with, there's lots and lots of things that can be done. We're going to go through one example in some detail, so this is going to be somewhat long. I will leave it to you to decide how you want to get through this in terms of splitting it up into manageable pieces instead of cutting it up myself. There is going to be at least one natural break point where we start talking about convolutions, so I'll let you know when we get there. But to start with, there's just a tremendous number of things that can be done with Fourier transforms, and this is particularly true in the realm of signal processing, where lots and lots of things have been developed for this. So there's lots of tools available within SciPy for dealing with these things, most of which we're not going to talk about or even use at all. But just to let you know that they exist, let's talk about a couple of modules that exist in SciPy. So one of them is Signal for signal processing. So let's import it and look at it. Okay, so signal processing. And there's a whole bunch of things in it. There's routines for dealing with convolutions that we've mentioned, various spline things, a whole bunch of filters, okay, ways of designing filters, okay, MATLAB related things, okay, and then various other useful routines, window functions, okay, various other spectral analysis, all kinds of important, useful things. Okay. We're not going to talk about those at all. If you are familiar with signal processing and or want to do more of it, then I strongly encourage you to look at what's there, what's available, how to use it. There's lots of documentation and examples online. So that gives us a lot of the extra support things that we need for processing signals using Fourier transforms. Oops. There's a Fourier transform set of routines in ffts. So let's look at this. This does discrete Fourier transforms. It implements the fast Fourier transform, various algorithms and specialized versions of them, various other support and related things. Convolutions are also in here. Some more underlying routines. Okay. So again, wonderful set of routines for dealing with Fourier transforms. And there's nothing wrong with using them, but we're not going to. This is one case where there's also FFT routines implemented in Numpy, and we're just going to use those. These provide a basic set of the simple things that we need and will be good enough for what we want to do here. So we're just going to stick with these. Okay. So if we look at the Fourier transform routines that are available, well, there's FFT that does the discrete Fourier transform, and IFFT that does the inverse. There's then two-dimensional and n-dimensional versions of these. Okay. There's then specialized ones for if you're just dealing with real functions, okay, or real discrete Fourier transform, or Hermitian, okay, if we have complex with certain properties. We're not going to use or talk about these, but again, these are very important and useful things because remember, the point of the Fourier transform and what makes the FFT so useful is that we can do it very fast, which means we can solve very large, complicated problems very quickly. And so having these specialized routines to make them even faster and even better in certain circumstances are quite useful. Okay. There's some helper routines, in particular this FFT freak we'll look at. Okay. And again, I will encourage you to look at all of these things in more detail as you need them or are interested in them, because it's a tremendously powerful set of things that we can do with these. There's then a long description of, well, what they call background information that should be consistent and similar to the types of things that we discussed. Implementation details, okay, various things about the real transforms, higher dimensional transforms, some references, and there's some examples in the various functions. Okay. So before we go ahead and use this, let's create some data to play with. So I've written a little, well, I've put together something here that will construct some random data for us. So we're going to construct for 10,001 points. We're going to randomly pick some frequencies or periods that are in our signal. So our signal is just going to be constructed of, in this case, 3 frequencies, okay, or 3 periods, 3 sine waves. In fact, they are sine waves, as we can see here, well, with some phase shift. But just 3 sine-like waves that are going to dominate our signal. And so that's what we're doing here. We construct random amplitudes for them. Okay, we pick random phases so we can shift our signal in time. Okay, and then we construct our signal. Here I'm calculating it by hand, basically. Okay, and then we add noise to it. Okay, we're going to add Gaussian noise, also known as white noise. Okay, we add noise proportional to our signal, and then we add some large background noise. Again, Gaussian random noise. Okay. If we know anything about signal processing, this signal is going to look strange, or it's going to look very noisy. So let's plot it first to look at it. So the temperature is a function of our signal. Notice our noisy signal is in Hn. We're going to plot it using the smallest markers. That's given by the commas, just so that it doesn't overwhelm the plot. So here it is. Okay. So here's our signal. Now the claim is that in this signal there's 3 frequencies that dominate. All the rest of this is noise. And our objective, at least to start with, is to find that signal. Okay. Now, we can sort of see that there's some structure to this, but to actually pick out the frequencies looks like it's going to be challenging. Okay. At least in the time domain, so this is time as a function of signal, or signal as a function of time, looks like that's going to be hard. And so this is where the Fourier transform is going to be useful for us. So to Fourier transform a signal, we use the FFT function in the FFT module. Okay. So what do? We feed it our signal. There's various things that we can pass to it, and what it returns is a complex array. Okay, again, talks about some other things that we'll see a little bit of. That's going to be the Fourier transform. Okay, tells us other things to look at, some documentation, gives its own example. Okay, so let's just call this capital Hn, and let's take the Fourier transform of our signal. Here it is. Okay. Now, one question is, how is it stored this information? Okay, if we look here, it doesn't tell us too much. It actually tells us to go back to FFT, a module itself, which we were looking at before, which tells us the definition and the conventions. Okay, so you can go back and look at that and understand what it's doing. But we've kind of discussed this, and we have positive and negative frequencies in there. And the real question is, how is this organized? Well, fortunately, there's a function that tells us this FFT freq. Okay, this returns the sample frequencies. Okay, and it returns them to us in the order in which they're stored in the Fourier transform. So in other words, we've gotten this result. Okay. This result is the Fourier transform. Okay, so this is the function, the Fourier transform, evaluated at certain frequencies. So this corresponds to one frequency, this to another, etc. How are these organized? And that's what this function does for us. It returns the frequencies. So we tell it how many samples we have. We can give it a step so that we can turn the frequencies into real physical things. It assumes a step of 1, in other words, that we sample every second. Okay. That's what we've done in our example, so we're not going to set this. But if we were sampling at different step sizes, okay, every 1/10 of a second, we would put 0.1 here, etc. And then the frequencies that we get back would be real frequencies. Okay, they'd be measured in hertz. Okay, and so we could directly compare them. For our purposes, we're assuming that we're just doing it, say, 1 second. So we run this, and it returns the list of frequencies. Okay, so let's in fact store that in something. Okay, let's look at it. Notice the first frequency is 0. Okay, 0 frequency is included. 0 frequency is called a DC offset because it's just a constant. Okay, or in other words, the cosine of 0 is just 1, so this just provides a constant and shifts things. The rest of the frequencies are stored as, notice there's a frequency here. Okay, this is our next smallest frequency. Okay. There's negative frequencies in here too, so there's also negative this value. Notice that's stored as the last value. Okay. Here's the next frequency. There's negative of this. Notice that that's stored as the second to last value. Okay. In other words, the frequencies are stored incrementally from 0 up to the n frequency that we have for n over 2. And then they're also stored, and then they're stored in reverse with negative signs, counting down, I guess, in magnitude, all the way down to this minimum value, which is the negative of this one. Now, whether that makes sense or not, it's actually a really smart way to store things. So suppose we want to skip the 0 frequency. That's just a DC offset. That's typically not interesting, so we typically want to ignore that. So we can get a list of the non-negative frequencies, not including 0. Okay. Those are stored from 1 to n over 2 plus 1. Okay. In other words, if I look at these frequencies, these start at the smallest one and go up to the biggest one. Okay. The nice thing about the way that this is stored and array slicing in Numpy is that if I, instead of look at index 1, 2, 3, etc., I look at -1, -2, etc., notice that these are exactly the same frequencies, okay, except with minus signs. So this provides a very easy way of indexing our Fourier transform, our capital H, and pulling out the frequencies that we want. So I recommend that you think about that and understand that, because this is a very powerful way of getting the information that we want. In particular, if we want to calculate the power spectral density, as we discussed in class, we saw that this was the sum of, this was the absolute value at frequency, at some frequency squared, plus that same contribution at the negative frequency. Well, now that's easy to access, okay, because we can easily index the results. So again, maybe it's best to just write it out. Okay. So if we start with this, okay, what is this doing? This is checking the absolute value of h of f, okay, capital H of f, as we wrote in class, squared, okay, for all the positive frequencies. If we're calculating the power spectral density as we discussed in class, we also want to add in all the negative frequencies. Okay, so if we want the contribution from this frequency and this frequency to be added together, that's exactly what this does. Okay. Again, think about it and make sure that that makes sense. Okay. So this gives me the power spectral density. Well, let's look at it. Let's not mess up our original plot, so let's make a new plot. Stick it over here. Okay. And so let's plot as a function of frequency at just the index value, so just the positive frequencies, okay, the power spectral density. And we'll just make it a black line. Okay, there it is. Okay. So notice, for the most part, it's pretty flat. Okay, this is actually showing all the noise. And there's some features down here. Okay, there's some spikes in this power spectral density at some low frequencies. Okay. Let's zoom in on that. And we see that there's 2 peaks here, okay, and then whole bunches of zeros. Okay, in fact, I guess if I shift this a little bit, we can see that there is all this other stuff here. These peaks then are representing the real signal, or at least we know it's representing the real signal, and all these other things are not. And so we can cut out all the noise by just taking the frequencies that contribute to our signal. In other words, we want, we can put some cutoff in this power spectral density to just pick out the frequencies that we want. Again, what does that mean? Well, that means use the where command. So let's only take the values from the power spectral density that are greater than some value. Let's try 0.4. Okay. Now, notice that this is 10 to the 12, so we really want 0.4 times 10 to the 12. And we see that there's actually 4 frequencies that come in, okay, whereas we claimed that there was going to be 3, so this is good. We'll be able to understand that. So let's save those. Okay. And now the question is, at what frequencies do these occur? Well, our guess might be at these frequencies. Okay. Well, that will be wrong. To see that that's wrong, let's actually look at where these frequencies occur. So let's draw a line at this vertical line at this frequency. Okay. Well, that doesn't seem to align with the peak. What happened? Okay. This is an important point. When we do something like the where command, what we're really doing is we're asking where in this array, what index values in this array satisfy the constraint. But what does this array mean? And in fact, how was this array constructed in relation to the frequencies? Well, it was constructed using these set of original index values, okay, which I've now overwritten, which was silly of me, so I'm going to have to fix that. Okay, and so really what it's doing is it's indexing things in terms of this list of indices. Okay, so let's say that again and try to make some sense of this. Okay, so originally we had written ind like this. So let's give that a new name and call that ind frequencies. Okay. This new list of index is actually relative to this set of values. In other words, if we these are the index values in the list of frequencies at which these spikes occur. So in other words, the actual list of frequencies are these, and if we were to draw vertical lines at these frequencies, we would see that they line up with where these peaks occur. Okay, so I encourage you to do that. Again, this is an important point, something that you need to be aware of and careful of whenever we use the where command. Okay, we have to know how we've processed things so we know what we're actually indexing. Whew. Okay, so with this in mind, we have these four frequencies. Okay. So let's construct a new HN. Okay, so let's make a I don't know, let's call it cut. Let's make this be zeros like our original HN. Okay. And copy into HN cut in the appropriate place. So that's at our frequencies. Okay. The values of HN at those points. Okay. In other words, we're just copying in these particular amplitudes, the contributions at these frequencies, and letting everything else be zero. Again, we need to be careful, okay, because it's not just these frequencies that matter. It's also the negative of these frequencies. Well, again, because of the way that this is stored, as discussed above, we can easily get those values by just copying in the negative index values. Okay. So now HN cut is mostly zeros, and there's only a few non-zero values. We can go back. We can go back by using an inverse Fourier transform. Okay, so the inverse Fourier transform looks exactly the same. Okay, notice it tells us that A0 should be the zero frequency term. The other ones should be the positive and negative frequencies. So that's what we did here to get the positive and negative frequency values set. So let's construct our new noisy signal, call it HN cut, by doing the inverse Fourier transform. Okay. So this is HN cut. Okay. So this is our new signal, which just contains this set of frequencies. Okay. Now before we look at this, we should be careful and we should worry. Okay. When we go from a Fourier transform to an inverse Fourier transform, we saw that there was this issue in the continuous case of 1 over 2 pi's. In the discrete case, there's this issue of 1 over n's. How is that handled? Okay. Well, if we read the documentation, it will tell us what that answer is. But what I prefer to do is to just do it. In other words, we have our signal. So let's replot it here in my temporary plot. Okay. I can inverse Fourier transform this, and we've already Fourier transformed this. I can calculate the inverse Fourier transform and see how it compares to this. Does it give me exactly this signal back, or does it give me this signal back scaled in some way by a power factor of n or 1 over n or something like that? Well, really the easiest thing to do is to just look and see. Okay, we don't really need labels on this. Okay. So capital HN was a Fourier transform. If I inverse Fourier transform this, it should give me HN back up to potentially some scaling. Okay. So we do that. Okay, warns me about imaginary parts, but don't worry about that. We were really dealing with a real signal, so we could have really used a real Fourier transform here. We've just chosen not to. Anyway, we see that it lies right on top. So the inverse Fourier transform does the right thing. It rescales things correctly. Okay. Again, there's no guarantee that any particular library or implementation you're using will do this. Okay, it's nice that this one does. What that means is that we can now plot this, let's call it, what do we call it, HN cut. Okay. We want to do this back on our original plots. Let's go back to figure 1. Okay. I don't know, let's make it a red dashed line. Let's make it a little bold so we can see it. Let's call this, I don't know, frequency cut. Okay. We plot our signal on there. Okay. So the claim is that this really is the underlying signal. All this other stuff is noise. And so just by doing this cut in frequency space, we've been able to cut out all this noise and get out the dominant underlying signal. It appears reasonable. Where the peaks occur here is where the peaks occur in the signal for the most part. Okay. In this case, we can actually compare this to the true signal because we generated this. Okay, so let's draw the true signal in here. Notice that it falls pretty much right on top. There's some slight differences, okay? And it's not surprising there's some slight differences because again, we've sampled this at finite time steps, so we aren't really getting the full information, but we've done a very good job of getting that information. So our just frequency cut signal does a very good job of mimicking the true signal. And so again, the frequencies that we deduced for our signal were this, just based on a cut in the power spectral density. The real frequencies were these. Okay. And so we see that this frequency is pretty close, this frequency is pretty close. This one kind of fell between two frequencies that appeared in our sample, and thus the power in this one got split between the two frequencies. And again, that just has to do with the fact that we're only sampling this at a particular rate, and so we can't turns out we can't perfectly match this frequency, or can't even get close enough so that most of the signal goes just into one of the frequencies we measure, and that's why this got split between two frequencies. Okay. Okay, so this is one basic type of analysis that we can do. Okay. The other type of analysis is convolutions, or that is smoothing the data. And so we're going to talk about smoothing now. Now we're going to go ahead and use the same data. So I'm just going to continue on, but you know, if you're worn out already from this discussion, you might want to pause now and come back to this. Okay, so let's continue on. So let's talk about smoothing the data. Okay, so let's use figure 2 for some of this. Now to smooth the data, you know, we have our original data. It's very noisy. Okay, there's lots of high frequency noise in this, lots of rapid oscillations, whereas our true underlying signal, let's suppose we know, is actually smoother than this. Okay, it doesn't have this high frequency noise. And so to do this, we want to smooth this in some way. Well, let's do this using a Gaussian function, Gaussian smoothing. So let's let our sigma be 100. And notice I'm being careful and to make it floating point. If we don't, we would run into problems. you can go ahead and do that and see that you run into problems. And let's consider a set of time steps from minus n over 2 to n over 2. Again, since we're using a time step of 1, you can think of this as minus n over 2 seconds to n over 2 seconds. Okay. Let's construct a Gaussian, okay, with this width centered on 0. Well, we know how to do that. A Gaussian is minus tt squared divided by 2 divided by sigma squared. Let's normalize it. The square root of 2 pi divided by sigma. Okay. So let's look at that just to make sure that we've done this correctly. This is always a good thing to do. And so we've constructed this Gaussian centered on 0. Okay. We want to convolve this with our original signal. Okay, we want to convolve it with this signal. Well, we've talked about how to do that. We've talked about we can do this in using Fourier transforms by just multiplying them. So we already have the Fourier transform of our data. Let's take the Fourier transform of our Gaussian. Okay. Okay. And now the convolution of these, let's just call it hg, is just hn times g. Okay. So there's our convolution. Okay. This is smoothing our function with a Gaussian. Of course, this is in Fourier space or in frequency space, so we want to transform back. So let's call this hn smooth 1. Okay. And this will be the inverse Fourier transform of our convolved signal. Okay. So let's not overwrite our original signal. Let's go ahead and make a new plot. In fact, let's just plot the true signal and compare to the true signal. We can compare to the data also, which is a good, nice thing to do, but here let's just do this. So let's look at the signal. Let's call it smooth 1. Okay, red dashed line. So it is smooth. It's not nearly as jagged as our original thing, which had all these crazy oscillations in it, but it doesn't actually seem to agree very well. Okay. So that's a problem. Okay. Okay, so before we understand what that is, let's also point out that we don't have to do this by hand. Okay, convolution is a very common thing, and we saw in some of the SciPy modules that there is convolution stuff. In Numpy, there's convolve, which does this for us. Okay, and as it says, this returns the discrete linear convolution of two one-dimensional sequences. Talks about what that means, often seen in signal processing. Blah blah blah. We pass in two things, a and v, and there's this mode thing, which I will let you read, which are details about how the convolution works. Okay, we're just going to use the default, which is mode full. Okay, and it also tells you that we can do this in other ways. Okay, so let's just go ahead and do it. Okay, so we convolve our signal hn with our Gaussian g. Notice that these are the functions in real, in the time domain. Okay, it gives us some answer. That looks a little strange. There's lots of zeros there. Well, let's call this hn smooth 2, and now we're concerned because there's lots of zeros in it. So let's look at it. Once again, let's create a temporary plot to do this for us. Let's just plot it. Okay, so there's a couple of interesting things to notice here. First, notice there are lots of zeros in it, but then there's a signal in it. Okay. Also notice that here there was 10,000 points, really 10,001 points, whereas here this goes up to something like 20,000. Okay. So it's extended the range. There's all these zeros in here, okay, but there is a signal that, if we look at it, doesn't look so different from this black signal. Okay. So what's happened here? Well, what's happened here, and again I'll encourage you to look at the documentation, is it's done what's known as zero padding. Okay. The problem with the calculation that we did here is the important point that the Fourier transform assumes that our signal is periodic. Okay. Again, let's think about that for a second. It assumes that it's periodic. Actually, we can look at it from here. So what does that mean? That means that when we're applying a Gaussian to this, we stick our Gaussian, which is some sharply peaked thing. It falls to 0 outside here. So inside regions here, so we're applying this Gaussian to this. Okay, the Gaussian in principle extends out to plus and minus infinity. How does it account for that? Okay. Well, when it extends beyond the edge of this curve, okay, beyond the edge of this, okay, it wraps around. Okay. In other words, it assumes a periodic signal, assumes that this signal repeats itself here. So that means that we take this and move it here, and then we get our little bumps and wiggles. Okay. It assumes that this repeats here, so it starts somewhere here and starts giving us our bumps and wiggles. Okay. And so what it's doing is it's mixing information from here into here, and it's mixing information from here over here, and it's spreading that out throughout our whole thing. Okay. To get around that, we use zero padding. In other words, we extend the signal, put zeros here, zeros here. Okay, it doesn't really matter how we zero pad. We just want to add a whole bunch of zeros here, and we want to add enough of them so that we don't get mixing of our signal from this wraparound. And so that's really what's being shown here. Okay, zero padding has been done to double the size of the array by adding a whole bunch of zeros. In the way that it's done it here with the mode full, okay, it's done zero padding in a particular way, I think at the end of the array, so that it moves our signal to the middle of the output. In other words, the real signal, or the signal that we want, appears in this case in n over 2 to 3 times n over 2. Okay, this is the actual signal. So if we go back to figure 2, which we were actually at, but let's be careful, and now we plot our new function. I don't know, let's make it a green dash dot line. Wait 2, call it smooth 2. Okay. Oops. Right. So that fails because smooth 2 is too large. So that was a good thing to do. Okay. We want just the region that contains our signal, which we said was this one. And we have to type things correctly. There we go. Okay, so there we go. Typed correctly. Now if we look at this green dash dotted line appears to agree much better with the black line. There's a few discrepancies. It shouldn't be perfect, okay, because there's still extra information here. We've smoothed with the Gaussian of a particular width. Okay, we're still getting some noise in here, but it does a much better job of mimicking the signal. To make that a little more clear, what's going on, so let me stick the legend in there just for fun. To make that a little more clear, we can do the zero padding by hand to see how it works out. We're going to do it in a slightly different way than it was done by Convolve. Okay. So again, what zero padding means is that we construct an array, let's call it HZ, okay, to be zeros of length 2n. Okay. Now we stick somewhere in here our true signal. It really doesn't matter where we stick it. It just needs to be continuous. Okay. Where we stick it is going to then reflect where it appears oh, sorry. Right. Sorry, that's fine. Where we stick it is then going to determine, where our final answer appears. Okay. So let me stick it, I don't know, in the end. So from n on. Okay. So let's stick our noisy signal in there. Okay. Again, let's look at this just to make clear what we're doing. And again, this is always a good thing to do, to pay attention. So what we've done is we've stuck our signal at the end of this, and we've stuck a whole bunch of zeros in here. Okay. So now if we Fourier transform this hz, take the Fourier transform of hz, of little hz. Okay. Let's construct a new Gaussian. So we want to construct our Gaussian over the same range. Don't really need to, but let's do it anyway. Okay. Let's Fourier transform that. Now we'll call this hzg, which is hz times g. Okay. So again, are now zero padded. Finally, let's call it new. Take the inverse Fourier transform of this, okay, and this should be our signal. Fourier transform, or sorry, doing this convolution via the Fourier transform by hand, but now with zero padding. Okay, once again, let's look at this before we stick it on our real plot. Okay, and here's our signal. Okay, and again, details that we're not going to sweat, because we stuck this at the end when we first constructed it. In the convolution, it's stuck it at the beginning, and so that was just for convenience. Again, it would be good for you to test if you instead fill in the first n of these with the noise. Where does it appear in here? Or if you do n over 2 to 3n over 2, where does it appear, etc. Okay. The point is that it will appear within a whole bunch of zeros. Okay, and so this is the signal that we want. So if we go back to figure 2, and if we plot on here, what do we call this? hz new. Now we can plot the first n of these. I don't know, we'll make it blue dots. We'll make it a little bit bigger. We'll call this zero padded. Okay. And let's see. Okay. Update the legend. We should see that this falls right on top of the green curve. Okay, in fact, it's entirely identical because in fact that's exactly what convolve is doing. Okay. So again, this is showing us what zero padding does to our signal. When we do a convolution, how this affects our signal, and how this gets rid of this wraparound or the periodicity of the signal, and accounts for it. Okay? And again, that's just something that we have to do when we're dealing with convolutions. Otherwise, we run into the problem that we saw here with this red dashed curve. Okay, now there's lots of other things that we can do. If we go back to this Fourier transform that we found before, back in figure 1, okay, what we've really done when we did this so-called frequency cut is we applied a filter, a frequency filter. Okay? In particular, what we're really doing is, well, applying a very special frequency cut wherein we pick out particular frequencies. A more general version of this is to apply some sort of window function to our data. And again, we saw in the signal module there's a whole bunch of window functions, and in signal processing you study what these various window functions do and why they're useful and whatnot. The most common thing and the simplest thing is just to do the so-called high pass or low pass filter, okay, which means you cut out high or low frequencies. Well, that's really easy to do in the frequency domain. We just take those frequencies and we zero them out. Okay. So let's make a copy of this. I don't know, we'll call it HN2. We'll call it HN filter, because we're going to apply a filter to it. So we make a copy of this. We need to do this, because if we don't, then we'll be overwriting the original. Okay. And let's apply some high frequency filter, okay, high pass filter. Now we know the frequencies that actually appear in our signal are not too high a frequency. Okay, this 0.0015 is the biggest. So let's apply a frequency cut of, let's say, 0.002. Okay, again, this is a somewhat arbitrary example, but just to get the idea. So what we want to do is we want to cut out all the frequencies larger than 0.002. Okay. Well, we can do that with the where command. We can ask, where is the frequency greater than 0.002. Okay. Well, if we do this, this isn't quite right, because remember there's positive and negative frequencies in this list. So it also cut out all the negative frequencies. Okay. Right, which of course is not, well, right. So this is, also not including all of these negative frequencies. What we really want is we want the absolute value of the frequency to be bigger than 0.02, and then we're going to want to cut these out. Okay. Well, we can do that, again, using the where command or using what we had seen in a previous lab. If we do this, this does the equivalent of just picking out these values, and we want to cut them out. How do we cut them out? Well, we set the amplitude of them to be 0. Okay. So we've now applied a high-pass filter. We've cut out all frequencies bigger than 0.002. Okay. Well, we can look at what the signal looks like by doing the inverse Fourier transform of this. Okay. Well, let's go back to figure 1 and plot in there. Let's see. We'll make. Let's call this. What was this? HN filter. I don't know. We'll use the green dash dot line since I like that one. We'll call this high filter. Okay, to just give it a silly name. And we plot that in there. Okay. Now this is kind of hard to see because this is kind of noisy, but let's put the legend in there. Okay. We might sort of be able to see it. We can improve this by doing things like, I don't know, let's remove the signal data. Let's make that invisible. So for those of you who were around after fall or right before fall break, you know how to do that. Okay, that makes sense to you. And so we made that invisible. Let's change the y limits. I don't know. Make it the same, I guess, as the other one. Maybe minus 600 to 600 to expand this a little bit. And we can see that by applying the high-pass filter, we have now this signal here, okay, this green dashed line, which actually does a pretty good job of mimicking the true signal. Okay, it's in some places different, in some places does a better job, in fact, even than just cutting out the frequencies as we had done in the first case. Okay. So again, this is a very simple example of applying filters in frequency space. There's a ton more that we can do with it, but through all of this, we're supposed to get a handle on the general procedure that we're following here. We can do things in the time domain. We can do things in the frequency domain. We can very simply switch between them by using Fourier transforms and inverse Fourier transforms. Some things are easy to deal with in the frequency domain, some things in the time domain. We can look at things in the different domains in different ways. And because we have this very fast way of converting between them, we can play these games as we wish. Okay, so that's, I guess, going to be it for this. Congratulations in getting through all of it.